Thank you. Yeah, so yeah, I was saying we're gonna we extended actually. We're gonna extend triple integrals over rectangles to triple integrals over elementary solids in the space, right? So elementary, so triple integrals over elementary solids in the space. Right. So actually, I defined. So on Tuesday, I defined the elementary solids on in the space. I think I gave just one example. I think that was the bowl of Redis one. But I'm gonna just remind you quickly, guys, the definition of elementary solids in the space, and I'm gonna give you more examples. All right. And then of course we're gonna define the integral of this the triple integrals over these elementary solids, right? So let me just remind you quickly. So so on Tuesday we said elementary solid in the space. So we have three different types, right? So so we have three different types of elementary solids. Solids S, let's say, in the space. Right, so let me just remind the definitions here. So we said type 1 would be, type 1 would be the solids S. So S can be described as the set of the points X, Y, Z. So we are in the space. So this is three-dimensional space. So we have three variables, right? X, Y, Z. So in type 1, we said the Z would be bounded between two functions of X and Y. So Z is between two functions of X and Y, right? And then the projection of the solid S into the XY plane would be an elementary region, right? So on Tuesday, I explained a little bit what will be what do I mean by projection of a solid into a plane, right? So we said the projection of S into the XY plane is an elementary region. Okay, so what do I mean by elementary region here? So we're gonna have like two different cases. So either X would be between two constants. So we're gonna have like two different cases here. Like the case where when X is between two constants, let's say A and B, and then Y would be between two functions of X, let's say beta X and alpha X, right? And so the other case would be when Y is between two constants, let's say C and D, and then X, of course, between two functions, two continuous functions on the interval CD, two functions of Y, so beta Y and alpha Y. All right. So that's the type 1 of elementary solids. Type 2, so you can guess, and as we discussed on Tuesday, so type 2 would be when, let's say, Y is between two functions of X and Z. So S can be described X, Y, Z, the set of points X, Y, Z, so that Y is now is bounded now between two functions of x and z, and then the projection into the xz plane. So xz plane means, of course, the y coordinate is 0, right? So the equation of the xz plane is just y equals to 0, right? So the projection is elementary. And so as in type 1, here we're going to have also like two different cases, z between two constant, x between two functions of z, or like x between two constant and z between two functions of x, right? And then there's a type phi, of course. That's when the x is between type phi. This is when s when s can be described as a set of points x, y, z, where x is between two functions of y and z, and the projection. And so this is part of the definition, of course. So you need the projection into. So in this case, that would be the y z plane. So this is when x is 0, right? Y z plane is an elementary region. Okay. Anyway, so this is just to remind you the definition. Now, for the examples, as I said, we had an example, just one example, I think, if I'm not mistaken. I think we had just one example on Tuesday with the ball. So let me give you more examples here. So example. So first example was the ball. So this was discussed on this Tuesday. Now, next example, let's say you have so example number 2, let's say you have the solid bounded by let's say the paraboloid. Okay, z equals to 4 minus x squared minus y squared. Okay, and say the planes and the plane. Let's say the plane, the xy plane. So the plane, let's say z equal to 0. Okay, so we have this solid bounded by the paraboloid z equals to 4 minus x squared minus y squared, and the plane z equals to 0, right? So of course, it would be a good idea to try to sketch this solid S. Well, I mean, we can do it. We can try to do it here. So for the paraboloid, guys, so what does it mean here, paraboloid? Well, paraboloid, this is like extension of parabolas to the three-dimensional case, the three-dimensional space, right? So if you take the section of this paraboloid, then that will be like a parabola. So if you try to graph this paraboloid, so I'm gonna probably try some experience here, guys. I'm gonna use there's some app online that we can use probably to graph surfaces in the space. Probably that would give you a better idea than my my graphing, right? So let me for a second try to share this app website. Let's try this. So it's called actually GeoGebra. Let's see this .org. Okay, let's see. Okay. So we're gonna need the 3-dimensional calculator. All right, that's good. All right, guys, do you see the app, the GeoGebra?
Yes.
Yeah, okay, perfect. Okay, that's good. So for example, so let me graph this. So we want to graph z, right? Z equals to 4 minus, and so then we said x squared, right? Minus, and then we have this y squared, right? So, okay. Oops, it's not times 2, it's squared there. Should be a square. All right. Okay. All right. Yeah, that's perfect now. Okay, so this is our you see this the red paraboloid? You know, if you take a section of this paraboloid, then it would be like a parabola, right? What do I mean by section? I mean, like if you cut your paraboloid, right, you're gonna get a parabola. So that's the first surface. The other surface we said it's z the xy plane, right? Z equals to 0. So z okay, now we have another equation, right? Z equals to 0. All right. Okay. So then our region, our solid S is the one bounded by. Okay, I don't know if let's see. I mean, you can probably see the region bounded by, the paraboloid and the xy plane. It's just the xy plane is just it's the blue plane. It's the blue one, right? And yeah. So that will be our solid S, right? It's bounded by the solid, the paraboloid and the xy plane. I don't know if we can zoom in. Let's see if I can zoom in here. Okay, yeah, I can do that. Sure, good. This is good. Oops. Okay. All right, I can move it, I guess, to the other side here. Anyway, so you see, guys, what will be our solid here in this case? So it's bounded by the paraboloid, and so it's inside the paraboloid, but it's also bounded by the xy plane, right? The z equals to 0. Okay. Okay, so that's our solid. Now, so let me come back to our board. Is there any question, guys? So you see, I mean, I guess you can use this GeoGebra. I mean, if for this 3-dimensional case, I mean, if you want to graph anything like a function of, function of 2 variables or wherever, I guess you can use this this app. All right, so let me just come back now to our board. All right, here we are. Oops, why do I have to log in again? All right, sorry guys about this. Can I log in again? Okay, perfect. Okay, just zoom out here. All right, so yeah, so let me write down again here our example. So we have this, we said I have this solid. So S bounded by z equals to 4 minus x squared minus y squared, and z equals to 0. So I mean, if you try to sketch the solid S, So we said you have this like this paraboloid, right? This one here. Right. This is our, so this should be 4 here. Okay, so this is of course x, this is x, y, and z. When x and y both are 0, z would be 4, right? The height z would be 4. Anyway, so so that's our paraboloid. Okay, and then of course we have the xy plane, z equals to 0. So it should be this one here. So here we have z equals to 0, and so our solid S would be the interior of the paraboloid bounded by the xy plane, right? So that's our solid S. Okay. I mean, I think sometimes, guys, it's really a good idea to try to sketch your region or your solid S, okay? Because I mean, actually, sometimes it's not obvious to find the bounds for your integral. So it will be a good idea to sketch your region or your solid, all right? Now, I'm going to describe S. So we know the S is bounded by this paraboloid and the xy plane. Now, so how do we find the bounds here, or how can we describe S? Well, so the idea here in this three-dimensional in the space in three-dimensional case would be probably a good idea would be first, for example, let's say you fix x and y. Let's say fix x and y coordinate, for example. Of course, you can also try to fix x and z or y and z. Okay, so here I'm just saying, for example, if you try to fix the x and y coordinates, for example. Okay, so what does it mean to fix x and y coordinates? Well, it means that, so once you fix x and y, so for example here, this is, you are in the xy plane. So you fix the x and the y. So you can take a point here in the xy plane. All right, and so you take this line here, this vertical line. So for this vertical line, the x and the y coordinate are fixed, right? Because the only thing here that varies is the height, right? So you see this this line here, this one here. So the x and y coordinate any point on this line, they are all the same, right? All these points on this line, they have the same x and y coordinate. Okay, only the height z varies, right? So that's what I mean by fixing the x and y coordinate. You can just take, you take a like a vertical line. Okay, so once you take a vertical line, then you can see. So for your solid S, so you have these bounds. So it's bounded by the paraboloid here, right? And it's bounded by the xy plane. Okay, so you have this, you have this segment here. So in the top, it's bounded by the paraboloid. So this is our z equals to 4 minus x squared minus y squared. And here in the bottom, it's bounded by the xy plane. So this is where z is equal to 0, right? So it means that your height z, it's bounded between z equals to 0 and z equals to 4 minus x squared minus y squared. Okay. So what I'm saying here, guys, so what I claim, or what I can deduce here, is that my z is between 0 and the 4 minus x squared minus y squared. Okay. So does this make sense to you guys? So you see, for example, so if you decide to fix first the xy coordinate, okay, and then look for the bounds for z. So what you can do is just take like a, take a vertical line, So this vertical line, of course, is gonna cross your solid like at this point here and this point here, right? So the top here, this point belongs to our paraboloid, right? The 4 minus x squared minus y squared. And the point here, this black point here in the bottom, it's supposed to belong to the xy plane. So that's where z is equal to 0. So you can say then, well, so then my height z or my coordinate z is between these two equations, the 0 and the 4 minus x squared minus y squared. Right? Does it make sense to you guys? I mean, I guess probably this example is not, it's not that hard, but we're gonna see later, I mean, different examples where it's not that obvious, right? Anyway, okay, so now once you fix your z, so what we are saying here is that z is between two functions of x and y, right? This is supposed to be like my h of xy, and this is supposed to be like my g of xy. Okay. So this remind us of this would be so this would be of type 1, right? That's where z is between two functions of x and y, right? So this is type 1. All right, so now next, what we do for x and y. So we have to find the projection of your solid S into the xy plane, right? So now we're gonna find the bounds. So now we want to find the bounds for x and y. Okay, so what we do is we project projection of our solid into the xy plane. Okay. So again, what do I mean by this projection? Well, so that's what I explained a little bit on Tuesday. So what you do is, okay, let me graph again the solid. So our solid S is supposed to be this one here. Right, this is supposed to be our solid S. Okay, so what do I mean by projection of S into the xy plane? So of course, here's my x, y, here's my z. So what we do, guys, is the following. So you are supposed to take all the points of S. So for example, you take this point in S, or this one here, or this one here. Okay, you are supposed to take all the points in S, right? And then you're supposed to take like the line which passes through your point and which is perpendicular to the xy plane, right? And then the intersection with the xy plane would be the projection of your point into the xy plane. So for example, let's say you take this point here. So you take the line which passes through this point, right? And which is, of course, perpendicular to the xy plane here. So this is this line here. All right, so then the intersection with the xy plane would be, let's say, this point, this blue point. So this point here, this is the projection of my yellow point into the xy plane. Okay. Now, if you do the same thing for all the points belonging to S, like this one here, you do the same. You're supposed to do the same. You know, this one here, you do the same. Here, the same. So then you take the set of all the points, all the projections. So like this, you're gonna get this projection here. If you take this yellow point, you're gonna take this. You're gonna get this projection, etc. So then the set of all the points, the projections, the set of all the projections, that will be your projection of S into the xy plane. So then if you take the set of all the projections of the points, then you're gonna get this disk, right? The interior of the circle. So this is the projection of S into the XY plane. Okay. So this projection of S into the XY plane, it will be just it's going to be just the disk, the interior of the circle, so it's going to be just you have this X and Y axis, and so you're going to get this disk here of radius 1. Sorry, of radius not 1, but of radius 4. Okay, because of radius 2. Thank you. Sorry, of course. So I'm saying, so here it's supposed to be 2. Oops, this is 2 here. This is supposed to be 2. So here it's supposed to be 2. Okay. 2. All right. So I mean, another way to do it is just to, we can take the equation of our paraboloid, right? We can take the equation of our paraboloid, which is the 4 minus x squared minus y squared, right? And then you can just, because, the xy plane, the equation of xy plane is z equals to 0. So you can set z equal to 0. That's the equation of the xy plane. Right? So if z is 0, then you're going to have, of course, 0 equals to 4 minus x squared minus y squared. And that's exactly your, that's the equation. That's the exactly your projection here. So this is, you're going to get this circle of radius 2. So this is 4 equals to x squared plus y squared. Right? So, okay, so now I have my projection. So now we know how to describe a disk or the interior of a circle as an elementary region. So there are 2 options here. You can say, oops. So we can describe the projection. So our projection would be, the projection is, so you can say, for example, x between -2 and +2, and y between negative square root of 4 minus x squared, or positive square root of 4 minus x squared. Okay, or of course you can just you can start with y, saying y is between 2 constant, -2, +2, and x is between negative square root of 4 minus y squared and positive square root of 4 minus x squared, y squared, sorry. All right. And of course, our projection is an elementary region, right? That's because, in order to have an elementary solid, you need the projection into your xy plane or your xz plane or whatever plane to be an elementary region, right? So projection is an elementary region. Okay. But anyway, so here I describe my my solid S as a type 1, right? Z is between 2 functions of x and y, and then the projection of the solid into the xy plane is an elementary region. Before moving to the next example or exercise, is there any question, guys? So you see a little bit how it works. All right. So then, before the examples or the exercise, I think probably I should define the integral of functions over these elementary solids. So let me okay. So let me make the following claim. So here's a theorem. So let's say we have this elementary solid S. So S is an elementary solid in this space. Okay. For example, suppose that S is of type 1. So suppose, for example, before that, well, we have a function f of 3 variables, of course. So suppose we have a function f of 3 variables, continuous, of course, on S. All right. Now, suppose that S, as I said, we have different types of elementary solids in the space. So suppose that S, for example, is of type 1. Okay, so S, let's say S can be described as set of x, y, z, z between two functions of x and y, continuous functions. So g and h of x, y, right? And then, so our projection, let's say into, of course, the projection into the xy plane is elementary region. And let's say your y is between two functions of x, so beta x and alpha x, and x is between two constant, a and b. Okay. So of course, beta and alpha, they need to be continuous on the interval AB. Anyway, then so the claim is that the integral of f over s so the integral of f of x, y, z over this solid S, okay, dv. This is, of course, dv. This is our volume element. Okay, so the claim is that this integral would be equal to so in this case, so your z is between two functions of x and y. So we start by integrating with respect to z. So we're going to have dz first, okay, and then here we're going to have g of xy, h of xy, right? So we integrate first with respect to z, because z is between two functions of x and y. Then our y is between two functions of x, so we integrate with respect to y. So here's dy between beta x and alpha x. So because x is between two constants, so the last integral would be with respect to x, okay? Because your x is between two constants, so x. So here we're going to have x, so it's between two constants. Okay, so whatever we have between two constants, that will be like the last, that will be like the last integral. Okay. So this is like for this type 1. All right. So when your y is between two functions of x and x between two constants, of course, if so in other case, for example, let's say I'm gonna just make one more example. Because in this triple integral we have like six different situations, right? So z between two functions of x and y, y between two functions of x between two constants. So this case. Next case would be like z between two functions of x and y, x between two functions of y, and y between two constant, etc., etc. Right? So we're gonna have like six different situations, right? I think probably I discussed this a little bit last on Tuesday. So we're gonna have like six different situations, right? So let's say you have the following situations. So for example, if let's say mark here, let's say S is x, y, z. Let's say y is between two functions of x and z, h of x and z, z between, or let's say x, x between two functions of y, between two functions of z, let's say beta z and alpha z, right? And z between two constant, right? Let's say r and s. Okay, so this would be like a type 2. But when you integrate, so let's say you have a function, triple integral of a function f over this region, this solid S, right? So then in this case, f of x, y, z. So in this case, first you integrate with respect to y, right? Because it's between two functions of x and z. So we're gonna have dy first. All right, so then you have x, so dx, and then as I said, last one would be the one between two constant, right? So in this case, that would be z. My z is between two constants, so we keep the z as the last integral, right? Etc. Etc. Right? So your integral is going to depend on your um, on the type of your elementary solid, right? Well, before the examples and exercise, guys, is there any question about this? Well, I know there are a lot of different cases, six different situations, but it's, well, as I said, you keep the last integral with respect to the variable between the two constant, right?
Excuse me, I have a question.
Yeah, please.
So yes, we keep the constant as the last integral, but
Yes.
What about the first and the second? For example, so we can write in any order or only in that order that is.
No. So the first integral would be with respect to the variable which is between functions of two variables. So like here, y is between functions of two variables. So that will be your first integral.
Mm-hmm.
Okay? Two variables, and then one variable, and then constant.
Okay.
Mm-hmm. Any other question, guys? All right. So let's move to the example exercise. So probably I would give this as an exercise, and then of course I'm gonna solve it, right? So exercise examples. All right. So the first exercise, for example, is the following. So S, let's say the solid S is the tetrahedron. So what do I mean by tetrahedron? Tetrahedron is a solid with four triangle faces. So this is a four. It has four triangle faces. So with vertices, let's say the origin 0, 0, 0, 1, 0, 0, 0, 1, 0, and then 0, 0, 1. All right, so let me just sketch this solid S. We can use we can use a GeoGebra for this, but probably I would do it later. So let me just first sketch for you this tetrahedron. So this is X, Y, Z. I'm gonna need the one here, one. There's one here. All right. Okay, so our tetrahedron would be, so the vertices are 0, 0, 0. So the origin, 1, 0, 0. So here's 1, 0, 0, 0, 0, 0, 1, 0, sorry. And then the height, 0, 0, 1. So the height Z is 1 here. So we're going to have, okay, so I'm going to just connect the vertices. Oops, here. All right, so you can see, guys, we have like four triangle faces. I don't know if you well, so the tetrahedron would be this solid S here. The inside of this region here, right? Well, I hope you see that this solid has like four triangle faces, right? Like there is one. Let's see, I'm gonna use the blue. There is one over here. There is one here in the bottom, right? One on this side, and there's the other side here, right? So like there are like four faces, right? All of them are triangle. All right. So does this graph make sense to you guys? I mean, I know it's a mess, but I can also try to use GeoGebra for this. If it's not clear, what do I mean by this tetrahedron S here?
No, I think it's fine.
It's fine. Okay. All right. So then, so what we're gonna do, guys? We're gonna evaluate. Let's say. So exercise. The question here is to evaluate. Let's say you want to evaluate the volume of this tetrahedron S. Okay. So let me just remind you guys, we discussed this on when I introduced triple integrals on Tuesday. Volume of the solid S. Just recall you the definition here. So we said the volume of a solid S would be equal to, and this is the volume, of course. The volume of the solid S would be the triple integral of the constant function 1, right, over S with respect to the volume element dV, right? So this is our volume element, of course. So this allows us to compute the volume of our solid S. Okay, so what I'm saying here, guys, is that the function you have to integrate is just the constant function 1. But the problem, of course, would be to find the bounds, right? Okay, so what we're gonna do, guys, I think I have like 2 or 3 exercises, 2 or 3 examples here, exercises. So I'm gonna give you a couple of minutes, to think about how can we find the bounds here in this case, and then I will solve the problem. Okay, so I'm gonna give you a couple of minutes to think about this problem. So the idea, of course, guys, would be to first we have to find the equations, the equation of the, the equation of the faces, right? Like like in my example with the paraboloid, where's the example of the paraboloid? Right here. So like in this example of paraboloid, we had like just 2 surfaces, right? We have this paraboloid. This one here, we said that's like z equal to 4 minus x squared minus y squared. And here the bottom is just the xy plane, so it's z equals to 0. But in this case, of course, the equations are like a kind of given in the problem, right? Though here it's not, you have to find by yourself like kind of the equation of the faces, right? You're gonna probably need to find the equation of a plane. So this is supposed to be from, you're supposed to learn this from in Calc 3, but I'm gonna remind you anyway how to find the equation of planes, right? Okay, so I'm gonna give you a couple of minutes, guys, to think about this exercise. So let me just write down here for you. Step 1, we need to find the equations of your bounds, so your faces here. And then in step 2, you can integrate. I think there's only one phase, which is the it's equation. It's not obvious. Uh, so you're gonna need to probably use some material from Calc3. But anyway, again, guys. So I posted homework number 2 today, yesterday, right? And it's due next. Homework 1 is due today. Homework number 2 is due next Thursday. And again, guys, if you have any question, please email me. I think finding the bounds is like it's like solving 90% of the problem. That's especially for the triple integrals. I think the hard part here is just to to find the bounds. Integration, if you are, I mean, I guess you are really good with the integration stuff. That part wouldn't be a problem, right? But the hard part here is really to find, I guess, the bounds. So I think this is kind of similar to the problem number 4 in the homework number 2. Right? Actually, problem 4 and 5. So I mean, truth to be told, I don't know the answer. I mean, I didn't actually solve the problem. So I don't know exactly the answer, but of course, this is a volume. So it should be, your answer should be positive number. So if it's not positive, obviously it's not, there's a mistake somewhere. Um, but it should be volume of this tetrahedron. Actually, we can actually it's not really hard to compute if you don't want to use the triple integrals. I think you can easily probably figure out the volume of this tetrahedron. But yeah. So all I'm saying is that your answer, it should be a positive number. If it's not positive, then something is wrong. I mean, this is like first example. I mean, it's probably you're gonna have you're gonna have like a hard time to find the answer because this is like first example. But with more examples, guys, you'll see it's not that bad. Uh, okay. I mean, if you got the bounds, guys, I mean, I think the integral is not really hard. Um, did anyone find the answer? The volume of this tetrahedron? All right. Okay, so probably I'm gonna solve this. All right, so first, guys, we have to find the equation of the faces, right? So as I said, actually the equations here are kind of straightforward, except one, probably just one face. So in the bottom, oops. So here in the bottom of the tetrahedron, that's the XY plane, right? So the bottom, what do I mean by the bottom is this face here, right? So that's just the XY plane. So equation of the XY plane, of course, is z equal to 0, right? Because any point which lies on the XY plane, the z coordinate, the height z would be 0, right? So the bottom is the equation of the bottom is just z equals to 0, right? Now, what about this? Let's say this left side here. The side which connects the point 1, 0, 0 to the 0, 0, 1. Right. So this face here, the one on the left, well, it actually it lies on the XZ plane, right? The XZ plane, that's the plane which contains the X and the Z axis, right? That's what I mean by the XZ plane, right? So the X, let me just write it here for you. So the XZ plane, this one here contains the X axis, and the Y and the Z axis. All right. So what will be the equation of the XZ plane? Well, in the XZ plane, any point in the XZ plane, the Y coordinate would be 0, right? So Y is equal to 0, right? So here, this face here, the equation of this face would be Y equals to 0. Now this is the face in the in the back. That will be the YZ. This face here, this one here. So this face lies on the YZ plane. So this is the YZ plane, which contains, of course, the Y and the Z axis. So there, the X coordinate is 0. So here, X is equal to 0. All right. Now the fourth face, the one which connects the point 1, 0, 0, 0, 1, 0 and 1, 0, 0. Sorry, 0, 0, 1. So let me just write down here for you the equations we have entered now. So we have z equal to 0. We have y equals to 0. We have x equal to 0. And then there is the fourth plane. The fourth face would be this one here. So this is 0, 1, 0. This is 1, 0, 0. And this is 0, 0. So the last face, or the fourth face, would be this one here. All right. So we have this plane which contains, so the plane here contains the points 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So the face or the plane passes through the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the question, of course, is what's the equation of this plane, right? So let me just remind you guys, this is from Calc 3. So how do we find the equation of such a plane? So let me just recall you here. Okay, so to find the equation of a plane, we need to find, passing through 3 points, let's say. So we need to find the normal vector, right? So to find the equation of a plane, let's say passing through let's say x0, y0, z0. We need to find the equation of the normal vector. So we need to find the normal vector to the plane. We need the normal vector n, let's say a, b, c, orthogonal or perpendicular, orthogonal to the plane. Right, so then to the plane, and then so the equation of the plane would be, so then the equation of the plane would be, once you have the normal vector, you have a point which belongs to the plane. So then the equation of the plane would be a x minus x0 plus by minus y0 plus c times z minus z0. The x0, y0, z0, that's the point of the plane. And the ABC, that's the coordinates of the normal vector, right? Sorry, it's equal to 0, yes. So now the problem, I mean, we have like 3 different points, not just one. We have 3 different points that belong to the plane. So the problem here is just really to find this normal vector n, right? Normal vector n, guys. So what we do, of course, is just I'm gonna need the cross product, right? So so you have these 3 points. Let's say this is 0, 0, 1. Let's call this point P. This is a point Q, P, Q, and let's say R, capital R. This is the point, let's say 1, 0, 0. All right, so let's take, for example, just example here, RQ, these 2 vectors, RQ and RP. Okay, so then RQ, the vector RQ would be, you take the terminal point minus the initial point, right? Terminal minus the initial. Minus the initial point. So like in this case, RQ, the vector RQ would be 0, minus 1. 0, let me write it down here for you just one time at least. And then 1 minus 0, and then like 0 minus 0. So this is like a negative 1, 1, 0. All right. So it's terminal point minus the initial point. So it's like the 1, 0, 0 minus, sorry, the 0, 1, 0 minus the 1, 0, 0. Now the other vector, it would be the vector RP. So RP would be just, negative 1, 0, positive 1, right? And then you're gonna need, so then the normal vector, so n, the normal vector would be the cross product of RQ with RP. Okay, I don't know how you learn to compute this cross product, but of course there's a formula. You can use a determinant, so that will be actually the determinant of the matrix. So you have like the vectors I, J, K. Then you have, let's say, the vector RQ. So that's negative 1, 1, 0. And then RP, so that's negative 1, 0, 1. Do you guys know how to compute this normal vector? I mean, this determinant of this matrix. I mean, do I need to go through the details here, or I can probably just, anyway, so this vector here. So for example, a first component of this vector would be like you take this I. This I means the vector 1, 0, 0. And then you take you like kind of like a cross multiply here. So it's like 1 times 1 minus 0 times 0, right? So that's equal to 1. Please let me know if you don't know how to do this. Please let me know, because you can probably have this in the in the homework or in the test, right? Of course, this is not about finding the goal here is not really to find the equation of the planes, but it's just a part of the problem, right? Then of course the second component, the j. So j here means 0, the vector 0, 1, 0. So either use a minus sign, or you just cross multiply. Here's the 0 times -1 minus this -1 times 1. So that would be +1. And then there's this k here. This is the vector 0, 0, 1. And here you cross multiply -1 times 0 minus -1 times 1. So that would be +1. So here, that's another +1. Okay, so then the equation of our plane. The fourth phase. So we said it's ax minus x0 plus b y minus y0 plus c z minus z0 equals to 0. So the ABC, that would be the components of the normal vector, right? This is like A, B, C here. X0, Y0, Z0, guys, you can just pick any point here. It doesn't matter which point you pick. You're gonna end up with the same equation, right? So let's say that this is X0, Y0. Here I'm gonna pick the point R, but again, you can pick any point lying on the plane. So here I pick this point 1, 0, 0. So my x 0 would be 1, this is 0, and this is 0. So anyway, so the equation would be 1 times x minus 1 plus 1 times y minus 0 plus 1 times z minus 0. So then you end up with x plus y plus z equals 2. So there's this constant -1 here. So if you move to the other side, it would be +1. So there should be +1 here. All right. Any question, guys, about this equation of this plane? Nope. Okay, perfect. So then now we are in position to find the bounds of our integral. So this is step number 2. Now I got all the equations I need. So now how do we find the bounds? So let me sketch my tetrahedron again, okay? Just to show you how to find these bounds in this case. So I have this point here, this point here. All right, that's my tetrahedron. Anyway, so for example, guys, as I said, as I did in the previous example. So first, so in this 3-dimensional case, what you have to do is you, for example, decide to fix x and y. You can also decide to fix x and z, or you can decide to fix y and z. It's up to you. And of course, depends on the type. You don't know, so you don't know exactly what's the type of this elementary solid, right? So first, you have to try. Like, so you can, for example, try to fix. So let's fix x and y first, and see if it works. Okay, fix x and y first. As I said, if this doesn't work, you can also decide to fix, for example, x and z, or y and z, and see if it works, right? So let's say we're gonna fix x and y. So when you fix x and y, it means that, again, so here's my, this is x, this is my y, here's my z. So if you fix x and y, it means you're gonna fix, let's say, a point here in the xy plane, And by fixing the X and Y coordinate, it means that you're gonna fix the line which passes through this point here, right? This vertical line. So what I'm saying is that all the points which belong to this line, all the points, they have the same X and Y coordinate, right? So for this line, so here X and Y are fixed. Okay, so what do I mean by X and Y are fixed? It means that all the points lying on this line, they have the same X and Y coordinate, have the same X and Y coordinate. Okay. So if you fix X and Y, you have to take just the orthogonal or perpendicular line to the XY plane. If you want to fix, let's say, X and Z, then you take the perpendicular line to the X and Z plane, right? You want to fix Y and Z. If you decide to fix Y and Z, then just take a line which is perpendicular to the YZ plane, etc. Right? So here I decide to fix first X and Y. So I'm going to take this line, which is perpendicular to the XY plane. Now, this line intersect my solid or my tetrahedron at 2 points. So I have here, I'm going to use a different color. So I have this intersection here, all right, and this intersection here. Okay. Probably it shouldn't be on this line here. So let's say if you fix another, let's say a line here with the same XY coordinates. So for example, fix this line here. All right. So then this line is going to intersect your tetrahedron at 2 points. Let's say you're going to intersect here and somewhere here, right? On the fourth face, right? Anyway, so the idea here, guys, of course, you're gonna take so your height Z is gonna vary. So your height Z in the tetrahedron is gonna vary between these 2 points, right? You have this segment here between these 2 points, right? This is this point here and the one here in the top. So the first point here, this point here belongs to the XY plane. That's where Z is 0, right? So here Z is 0. So here my Z is 0. Right now, the other point, the intersection of my line perpendicular to the XY plane with the tetrahedron, this point will belong to the fourth face. Okay. And the fourth face, the equation of this fourth face is just this X plus Y plus Z equals to 1, right? So this is X plus Y plus Z equals to 1, all right? So the other point here, this intersection shouldn't be here. It should be probably somewhere, here. So the intersection would be probably somewhere here. So it's going to intersect this fourth face, right? This X plus Y plus Z equals to 1. All right. So my height Z, this is my height Z. So my height Z is going to be between these two equations, right? Between the Z equals to 0 and the Z equals to 1 minus X minus Y. Okay. So here, of course, if you solve for Z, so my height Z would be between 0 and 1 minus X minus Y. So Z between 0 and 1 minus X minus Y. Okay. So again, guys, what I did here, I fixed my X and Y. So once you fix an X and Y, so you have this perpendicular line to the XY plane. And then this perpendicular line to the XY plane would intersect your solid into 2 points, let's say. Okay, and then you have to find the equations where these 2 points belong. So like here, the point in the bottom belongs to the plane X, Z equals to 0. The point in the top would belong to the plane x plus y plus z equals to 1, right? So then I solve for z, and then I got the bounds for z. So my z is between actually two functions of x and y here. So this is like g of x and y, and this is like h of x and y. Okay, so this is the first thing to do. Find the bounds for z. I got the bounds for z. Now, next thing is, you have to find the bounds for x and y. Now, how do we find the bounds for x and y? We have to project our solid, right, into the xy plane. So now next, so we have to find the bounds for x and y. So to do that, we have to find the projection of the tetrahedron of the solid S into the xy plane. And in order to be an elementary solid, this projection should be an elementary region of the xy plane, right? All right, so now how do we find this projection of S into the xy plane? Again, it's just well, we are supposed to there are different ways to do it. Actually, I mean, geometrically, again, all you have to do is just so this is your y, this is x, this is z. So you have your tetrahedron. Okay, so to find the projection of your solid into the xy plane, so what we're supposed to do is to take all the points which belong to this solid S. So for example, this point here in this in the solid S, and we have to take this perpendicular line passing through the point, perpendicular line to the xy plane passing through this point. So that would be, for example, that would be this line here. If you take this line here, so this will be the projection, right? And you are supposed to do the same for for all the points in the solid S. And then the collection or the set of all the projections, that will be your projection of S into the xy plane, right? Or you can just, in this case, you can just xy plane, that's where z is equal to 0, right? So you can just say, well, you have so z is equal to 0. So then, you have this x plus y plus z equals to 1. So this equation becomes x plus y equals to 1. Okay. So actually, the projection of S into the xy plane would be this, the inside of this triangle, this one here. So this green triangle, that's the projection of my S into the xy plane. That's the projection of S into the xy plane. Okay, so if you just use the xy coordinates, I mean, this is very detailed explanation, guys. I mean, we are really doing all the details here, but it seems like it's a lot, but I mean, it's just because probably I'm giving too many details, so you can understand exactly what we are doing here, right? How to find these bounds, because again, sometimes it's not that obvious, I would say. All right, but anyway, so so if you use just the x, sorry. So if you use just the x and the y axis, right? So we would have the point. We would have this point here, right? This point here. So this is supposed to be 1, 0, 0. This is supposed to be like 0, 1, 0, and this is the origin, right? So we have our origin. We have this is supposed to be like 1, 0 or 1, 0, 0. So in the x, just if you use it just to coordinates, that will be the 1, 0. And here, this will be just the 0, 1. Right, so here's my projection. right? So this is inside of this triangle, right? Now inside, so this triangle, of course, this line here, the equation of this line would be just, x equal to 0. This line here is just y equal to 0. And this line here, this is the line which connects the 0, 1 to 1, 0, right? So you can just compute the equation of this line. It's just x plus y equals to 1. All right. So now what will be the bounds for x and y? So if you decide first to go with y, I mean, it's up to you, of course. So you can say, so like there are two cases here. If you go with y first, then you would say, so then y, the height y, is between, between these two lines, the height, it's between this y equals to 0 and this line here, y equals to 1 minus x, right? So your y is between, 0 and 1 minus x. And then, of course, your x coordinate would be between the 0 and 1, right? So between x is between 0 and 1. So x is between 0 and 1. Or you can, if you want to start with x, you can say, well, x is between 0 and 1 minus y, and y is between 0 and 1. Anyway, it's up to you guys. You can describe either way this triangle, right? But the point is that this projection is an elementary region, right? So that's why our solid S, our tetrahedron, is an elementary solid in the plane. Anyway, so we got the bound, so we are good now. We can integrate, right? So we can finally integrate after 20 minutes, I guess. Anyway, it's just you will have also some similar problems in the homework. And if you have a trouble with the bounds, again, guys, try to follow the same steps that I did, right? It's anyway. So the volume. So the volume of S of the tetrahedron. So the triple integral over S. So we said Z is between two functions of X and Y. So we start with Z. So Z is between two functions of X and Y. So Z between 0 and 1 minus X minus Y. So this is 0 here and 1 minus X minus Y. All right. And then we have to integrate with respect to, let's say, for example, well, you have two options here. Either you go with Y or you can go with X. So if you go with Y, so Y is between two functions of X here. So we integrate with respect to Y between two functions of X. So 0 and 1 minus X. Well, of course, 0 is just the constant function, but you can also say that 0 is a function of X, or it's a function of XY, or wherever, right? So when you have a constant function, it's just a constant function, right? And then, of course, the last integral would be with respect to the variable between the constants. So for example, here my X is between 0 and 1. Right? Or again, guys, you can interchange X and Y here. And of course, you have to change the bounds. Anyway, so if you integrate, so 0, 1, 0, 1 minus X. So as I said the last time, triple integral. So first we integrate with respect to Z. So integral of 1 constant with respect to Z is just Z, evaluated between 0 and 1 minus X minus Y. Right, dy dx. Oops. Right, so then this is 0, 1, 0, 1 minus x. So just substitute z with the 1 minus x minus y, and then with 0. So I'm going to get just 0, dy dx. Now we're going to substitute, we're going to integrate with respect to y. Okay, so this is, we keep the integral with respect to x, integral of 1 with respect to y, it's y minus, integral of x with respect to y. So x is supposed to be a constant. So there'll be the constant times y. So my constant is x times y minus, and then integral of y is just y squared over 2 between 0 and 1 minus x. Well, hopefully this integral is not too hard to integrate. Let's see. So we're going to have 0, 1, substitute y with 1 minus x. So that will be 1 minus x times 1 minus x. So we substitute again y by 1 minus x minus 1 minus x squared over 2 dx. Of course, you should substitute y by 0. Everything is going to be just 0, right? So I'm gonna just I'm gonna simplify first, guys, before integrating with respect to x. I'm gonna just simplify. So let's see, 0, 1. So let's see. So we have 1. Let me just distribute first. I can make easily mistakes, so I'm gonna just go easy here. So minus x plus x squared. Then minus 1 minus x squared you distribute. So this is just a half plus, minus x squared over 2. And then you're supposed to have minus 2x with a minus, that will be a plus. So that will be plus 1, right, dx. If I'm not mistaken, of course. I mean, please let me know if I did any mistake. Anyway, so this is 0, 1. So let's see how many x squared. So we have x squared minus x squared over 2. So that'll be x squared over 2. Sorry, I'm gonna just use the black here for them. Okay, so this is x squared over 2. X's, how many x's we have? Here, minus 2x. All right, so minus 2x. Oops. This is minus 2x. I'm sorry, minus 2x. And then what else? The constant. So we have here 1 minus half. That's plus 1/2. Right? Did that? No, sorry, I forgot. There's 1 here at the end of the integral. I forgot this 1 here, right? So half plus 1, of course, that will be 3 halves here. Sorry, guys. All right. So okay. So now I integrate with respect to x. That's not too bad. So x squared, that will be x cubed over 3. So that's x cubed over 6. And the integral of 2x is minus 2x, that will be minus x squared, and plus the half times x, evaluated between 1 and 0. So I'm going to just substitute 1 here. So 1 over 6 minus 1 squared plus 3 halves. And then, of course, substitute x by 0, you're going to get just 0. So this is 1 over 6 minus 6 over 6 plus 9 over 6. So the answer, so final answer, I hope I didn't do any mistake. But the final answer, it's 4 over 6 actually. So it's 10 minus 6, so it's 4 over 6, and that will be 2/3. Okay, so as expected, I would say at least I have a positive answer. That's good. But so yeah, so the answer is I think it's 2/3, and that will be the volume of our tetrahedron. Any question, guys, about this example? I mean, I would say the problem here is really to find the bounds. That's like the hardest part here. But otherwise, once you get the right bounds, then you're good to go, right? Is there any question about this particular example before the next one?
No.
No? Okay. I mean, all right. Okay, here's another example, guys. I'm going to give you a little bit of time to think about this example, and then I'm going to solve. All right? So example number 2. So let's see. And again, I mean, I don't know the answer. I'm not sure about the answer. I mean, I didn't solve the problem before, so I don't know exactly the answer. But here's the problem number 2. So the S is the solid. I think I'm gonna use the GeoGebra, the app here to graph this solid. But anyway, so the solid here S is bounded by. So we have the cylinder. Y squared plus Z squared equals to 9. And then the planes X equal to 0, Z equal to 0, Y equals to 3, and Y equals to 3x, right? So let me just explain here this equation of the cylinder. So if you want to graph a cylinder in the 3-dimensional space, so the idea, guys, is that, I mean, so you have this, you know, you have this three coordinates, X, Y, and Z, all right? So you want to graph, right? You want to graph Y squared plus Z squared equals to 9, right? I mean, Y squared plus Z squared equals to 9, it looks like a circle of radius 3, right? But in 3-dimensional space, because we have 3 variables, it's not just a circle here, because the X here, there's no X, right? No X. So if there's no X, it means that X could be anything, right? So X could be anything. It could be any number, right? The X coordinate could be any number. So we have this Y squared plus Z squared equals to 9, which looks like a circle. But the thing, it will be a circle it's a circle in the YZ plane. So this is a circle of radius 3 in the YZ plane. YZ plane. So again, when I say YZ plane, that's the plane which contains the Y and the Z axis. So it will be a circle in the YZ plane. But so here, right, I have this circle in the YZ plane. But the thing is, the X coordinate could be any number. So which means that you can extend this circle along the X axis, right? So you can extend the circle along the X axis and you're gonna get a cylinder, right? Probably here, this is really kind of bad here. This one here should be like this here, right? So you see the idea, guys. For example, so we wanna you wanna graph this cylinder. So you start with a circle in the YZ plane, and then you extend it to along the X axis, right? So you're gonna have like a bunch of circles along the X axis, and so if you connect all these circles, you're gonna get your cylinder, right? Well, anyway, yeah. So the question here, so this is my solid. Probably. So the question, of course, is to evaluate, let's say, the volume of the solid S, but probably I'm going to use GeoGebra for this because it's not clear here. So I'm going to just stop sharing the board, guys, for 1 second. And I'm going to go with this website, GeoGebra. Let's see here. All right, so just to sketch the graph of this solid S, right? It's all right. So we're gonna go with the 3-dimensional. That's no, here, 3D calculator. Okay, so you can enter like this first the equation of the cylinder, right? So let's say you have this Y square plus this z square equals to, sorry, it's z square. Okay, equals to what? 9, yes. All right. Okay, perfect. So you see the cylinder here, right, along the x-axis. So I guess here the x-axis is the red axis, right? It's like you have this cylinder along the x-axis, which is the red axis. Okay, so that's the first equation. Now next equation is x equal to 0. That's kind of that's just the yz plane. So x equals to 0. All right, so this is x equal to 0. That is the y z plane. So you see this y z plane, this blue plane. So it contains the z axis, which is the height, and it contains the y axis, which is the green one. Right. So that's my x equal to 0. Next, we said z equals to 0. Z equals to 0. All right. Okay. Okay. Probably I need to change the color for z equals to 0. So we have the cylinder. It's red. We have the x equal to 0. It's the blue plane. So I'm gonna change the color for the z equals to 0. So let's go with the yellow.
Excuse me, Professor.
Yes.
I don't see any picture of the graph.
You don't see the graph?
Yes, I mean I see the GeoGebra and the equations, but I don't see the graph itself.
Oh, really? What about you, David?
Is it right above the purple line?
Yes.
Oh, yeah,
Above.
we don't see anything there.
Oh, okay. Okay, I'm sorry. What about now?
It's white,
No.
blank.
Yeah,
It's-
now it's
It's
blank.
just the white
It's a
page.
blank?
I see the bottom purple bar at the bottom, but that's it.
Yeah,
Just,
yeah.
Nothing.
okay, just the bottom, the purple bar in the bottom, right?
Yeah.
Yes.
Okay, how does this work? I'm sorry, guys. I mean, this is like my first experience with this app.
You see something?
Yeah, of course. I see
Okay.
the whole thing. I see the whole graph, but I'm stop sharing.
There are
shared
some
it.
apps that can't be screen shared. Like sometimes Netflix doesn't work on Zoom, so maybe this app doesn't work.
It doesn't
Okay,
work.
just continue though. We could use this, right?
Okay.
GeoGebra. We could use it,
Yeah,
download it. Okay,
yeah.
that's
Okay,
fine.
perfect.
Continue.
I'm sorry, guys. I thought it works, but I'm sorry.
It's okay.
Probably I should find another app. All right, sorry about this. Okay, so let's come back to the board then. Website. This is really sad. Okay. Com. That's weird. I mean, okay. Anyway, yeah. So what we were saying, guys. Yeah, we have this solid S. I mean, I'm gonna try to do my best to sketch this solid S, but you know, it's gonna be a mess, of course. So solid bounded by. So the cylinder. Sorry, the cylinder was y square plus z square equals to 9. So we have the planes. So cylinder and the planes. So we had x equal to 0, z equals to 0, y equals to 3, and y equals to 3x. All right. So roughly, I mean, the sketch of of the solid S would be like something like. So this is y-axis, x-axis, the z-axis. So we're gonna have here, we're gonna need 3 here, right? And here we're gonna have, I'm gonna need 3, I guess, because this is 0, 0, 3. And we're gonna need what else? A 1 here. I'm gonna need 0, 0, 1. Sorry, 1, 0, 0. All right. Okay. So I'm gonna need this point right here. So this is the point 1, 3, 0. All right. So then the solid S would be like okay, so we have here like a cylinder. We have this line here, here intersection with the 3x. And then this is the line or the plane y equals to 3x. Okay, so so just to give you an idea here, guys. So this line here, this should be the line y equals to 3x. Right. So here, this line here belongs to the plane y equals to 3. This is y equals to 3. And then in the top, we're gonna have square root, we're gonna have the cylinder. So here, in this part here, this is our cylinder. So y squared plus z squared equals to 9. All right. And of course, in the back, we have, we have the x equals to 0. So in the back here, in the back here, that's x equal to 0. So the equation, anyway, so sorry, not the equation, but the question is to find, so the question is to find the volume, or let's integrate some random function here. Let's say evaluate, for example, the triple integral over the solid S of the function, let's say the function z. Okay. So, okay, so, we don't have time. So let me just explain the steps here very quickly, guys. I'm gonna come back to this, I guess, on Tuesday. But very quickly, guys, I'm sorry, I'm gonna go over time a little bit, but just very quickly, just explain the steps here. So the steps, first, of course, you have to find, well, actually, you have all the equations you need. So we have to find the bounds, right, for the bounds for x, y, z. So y, z, and then of course, and then you can integrate. So step number 2, and then you can integrate. Anyway, so I'm gonna do this next time, guys. This is kind of similar to the problem 4 and 5, I think, in the homework number 2. I mean, next Tuesday we still have time. I mean, the homework is due on Thursday, right? So I'm gonna explain this in more details next time. All right. So and then once we are done with this, and then we can move to the next section, which is a change of variables. Then we're gonna be done with the triple integrals, and then we can move to the change of variables. All right, guys. I'm gonna stop here, I guess, and I would see you next Tuesday. All right. So again, guys, if you have any question, please just email me. All right, anytime. And I will see you on next Tuesday. So stay safe and warm, of course.
Likewise.
Too
Thank
cold
you.
outside,
You
right?
too. Yeah.
Thank you, guys. Appreciate. I'll
Okay.
see you next Tuesday. Take
Thank
care.
you. Goodbye.
Me too.
Goodbye.
Bye, Professor.
Bye.